Hello everyone, my name is Jaeok Choi and I'm a PhD student at Stanford ICNE. This is joint work with my advisors Daniela Saban and Gabriel Weintraub at Stanford GSB on the design of optimal pay-as-bid procurement mechanisms. So let us first motivate our problem of interest. Due to the advancement of logistics operations and information and communication technology, two-sided online platforms have been replacing the role of traditional supply chains that had many middlemen. As the sole intermediary, a two-sided online platform must decide its market rules, including which of the participating suppliers' products are showcased to buyers and at which prices transactions happen. Since these platforms are driven by direct participation of suppliers and buyers, market mechanisms must be simple and transparent so that the participants can understand and trust them. In practice, this urge for simplicity results in market mechanisms being pay-as-bid mechanisms where suppliers choose the prices of their own products and the platform only decides which products are shown to buyers. In more detail, let's consider a platform in which buyers with heterogeneous preferences purchase from suppliers offering differentiated products. In this market, suppliers choose the prices of their products and submit them to the platform. And then the platform selects a subset of the products and shows them to buyers along with the posted prices. Finally, buyers purchase their most preferred option among different alternatives in the assortment. Such type of purchases are seen in many real-world examples, including online marketplaces such as Etsy and Thumbtack, group buying practices like drug formularies managed by insurance companies, and public procurement, where this work was mainly motivated from. Although the exact objective each of these platforms want to achieve might be different, in high level, they want to achieve low prices and enough variety for heterogeneous customers. But these objectives are typically in conflict with each other. When the platform decides to make the assortment decision more selective, price goes down due to a higher degree of competition, but the variety also goes down. So it is uncertain what is the optimal level of competition for assortment decisions. In this work, we consider the question that asks, how do we design practical rules that decide which suppliers are shown to buyers? And how do these rules affect prices? When we say practical, we mean the assortment decisions that meet the following three constraints. First of all, the mechanism should be implemented as pay-as-bid, which simply means that the price has to be what the supplier submits. This way, the participants easily understand the rules and they don't feel rigged by the platform. The second one is anonymity, which just means assortment decisions should only depend on prices, not the identity of the suppliers. There are two reasons why we put this constraint. First, it might be the case that the platform does not have enough information other than the prices about the suppliers to make an informed decision using information other than the prices. Also, in some cases, such platforms might be prohibited from discriminating a supplier over others. Lastly, we put a technical constraint called monotonicity that makes sure that when a supplier submits a lower price, he gets more demand allocated. There are many previous literature that motivated this study, but for the interest of time, I'll only briefly mention one work from which we borrow some result. Saban and Weintraub 2018 considers a more general setting and identifies the optimal assortment mechanism without the aforementioned practical constraints. They also propose different types of pay-as-bid mechanisms. The optimal assortment mechanism that they provide serves as an important upper bound for assessing the performance of possible mechanisms, but the optimal one itself is not very practical to be implemented. Moreover, the pay-as-bid mechanisms that they provide are intuitive and easy to be implemented, but their performance is not quite optimal. In this work, we characterize the optimal pay-as-bid mechanism. Throughout the talk, I'll introduce a simple class of mechanisms called sub-reserves and show its optimality under symmetric general affine demand models. Then we'll show the robustness of sub-reserves under different types of model misspecifications. Lastly, we will present the performance of the sub-reserves and their natural extensions with more general demand models. Now, let me introduce the model specification and assumptions. There are three kinds of agents in this work: suppliers, the platform, and buyers. First, there are n strategic suppliers, each offering one good. Each of them has per unit cost that could be either theta L or theta H. The distribution is known, but the realizations are private. They have no capacity constraint, and the result that we have can be generalized to any cost distribution with discrete support. Their pricing strategy consists of how much they price their product when they are of each type, and we denote them as BIL and BIH for each supplier I. They're risk neutral, and they try to maximize their expected profit. Next, we have the platform trying to maximize the expected consumer surplus. Given the prices from suppliers, they decide which products would be in the menu, and that decision is encoded as an assortment mechanism. This mechanism has to satisfy pay-as-bid, anonymity, and monotonicity constraints. In addition, we assume that it can assert the reserve price of R. Lastly, we have a unit mass of customers with heterogeneous preferences. An affine demand model outputs the aggregate demands as a function of prices, and they take the form of alpha minus gamma times P, where alpha is a vector of quality, and gamma is a matrix of substitution pattern. Generalized affine demand model extends this to accommodate two things. One, there is no outside option, so that the total demand adds up to 1. And two, they avoid negativity by allowing zero demands. This aggregate demand is common knowledge in our model. Now, let us take a look at the mechanism design formulation of this problem. We focus on the case where suppliers are symmetrically horizontally differentiated, which means alpha is just a multiple of one vector, so there is no vertical difference in quality. And in gamma, all diagonal elements and all off-diagonal elements are identical. Given an assortment mechanism, we restrict our attention to symmetric Bayesian-Nash equilibria, in which the strategy of each supplier is identical. Let x of q be the allocation function specified by the assortment function q and the underlying demand model, and cs of x of p be the consumer surplus with allocation x and prices p. The mechanism design formulation for the optimal pay-as-bid mechanism that satisfies monotonicity and anonymity is as follows. In here, we're finding the assortment function q that satisfies monotonicity and anonymity with reserve price R, and the corresponding equilibrium pricing strategy beta that satisfies the base Nash constraint and individual rationality constraint to maximize the expected consumer surplus. Now, note that the pay-as-bid constraint is already embedded within the formulation, as the prices are the bids of suppliers. There are few challenges associated with this formulation. First of all, we cannot use standard techniques in mechanism design because the payment rule is fixed as pay-as-bid. In fact, it is not even incentive compatible. Also, it is difficult to solve this problem as LP because generalized affine demand model gives nonlinear demands. In order to solve this mechanism design problem, let us define a class of assortment functions called K sub-reserve rules. Here is the definition of K sub-reserves. What it says is that if there are at least k suppliers pricing at less than or equal to S, only those suppliers are in the assortment. Otherwise, everyone pricing less than or equal to R is in the assortment. The parameter K decides how much emphasis the rule gives on having more variety versus creating price competition. And the parameter S splits the pricing space, and it induces suppliers to bid at S if possible. Here is an example of a two-soft reserve when there are three suppliers. When there is only one supplier who prices below 2, when there is only one supplier who prices below S, then we include everybody in the assortment who prices less than or equal to R. But if there are 2 suppliers who price below S, then we only include them in the assortment, even if the other supplier prices less than R. It is easy to check that the soft reserve rules satisfy anonymity and monotonicity, and it is also important to note the no competition mechanism, which puts everybody in the assortment, regardless of the price, as long as it is less than the reserve price, is a soft reserve rule with the parameter K equal to N, the number of suppliers. This mechanism often happens in practice, and we'll use it as our laissez-faire lower bound for performance comparison. So here is our main result. What it says is that any optimal pay-as-bid assortment mechanism with anonymity and monotonicity can be replaced by a K-soft reserve rule. Then we have another main proposition that says that the hard reserve price for an optimal pay-as-bid assortment mechanism should be theta H. This implies that given a set of primitives, an optimal practical assortment mechanism can be characterized via optimizing over the set of K sub-reserve rules with hard reserve price theta H. We can do this by finding the optimal value of S for each K and compare the objective among them. The best soft reserve rule with optimal K and S is an optimal pay-as-bid assortment mechanism. Now, let us take a look at the performance comparison among different best K sub-reserve rules for each K. The x-axis is differentiation cost, which tells how sensitive buyers are in regards to horizontal differentiation, which can be computed from the substitution pattern. As the differentiation cost increases, products become less substitutable, and yellow dashed line is the expected consumer surplus with the optimal mechanism, which is not necessarily pay-as-bid, and the gray line is that of no competition mechanism. And here is the performance of best K sub-reserves with different values of K. Note that as the differentiation cost increases, the optimal value of K increases as well. From this, we can compute the optimal pay-as-bid assortment by optimizing over K. We can see that it significantly improves over no competition, and it is even comparable with optimal, which is the outcome under the platform that can directly control all locations and prices, while the platform in our setting can only control the assortment. We also have the results for more general cost distributions. When there are n possible types, we can define analogous rule by splitting the pricing space more finely and deciding when to include all suppliers or not. But for the interest of time, we'll just skip this result. When implementing K sub-reserves in practice, there are a few problems. It might be difficult to accurately specify all the model primitives, which can lead to incorrect estimation of optimal parameters. Also, especially when M is large, estimating all parameters is computationally challenging and very error prone. so low-dimensional approximation might be desired. Luckily, K-soft reserves are robust to such model misspecifications. First, the soft reserve performs alright when S is overestimated. So here is the case with two suppliers, and the best soft reserve is the orange line. When we use higher value of S than the optimal S, the performance can still be much better than the no competition mechanism. Also, when there are three possible types, the best generalized soft reserve is as follows. But if we suppose that there are only two possible types and use a single S to split the pricing space, the performance degradation is actually not that much. Lastly, we looked at how K-soft reserve would perform with asymmetric demand models. Let's consider the two supplier case where one supplier produces superior product than the other. And as you can see, the performance gain deteriorates as the quality difference increases. And this is because the optimal mechanism is not anonymous. In an attempt to solve this problem, we can relax the anonymity constraint with partitioned anonymity. Simply, it takes a supplier partition and make the assortment fair only among the suppliers in each subset, not among every supplier. This might be useful because in practice, it is possible that the platform can only roughly differentiate suppliers. With this relaxed constraint, we can consider an extension of sub-reserves called partitioned sub-reserves. Here, we first run a separate K sub-reserves among suppliers in each subset of the given partition. Then we create an assortment of suppliers by adding all the suppliers chosen in their respective K sub-reserves. In the setting with 4 suppliers, where the first 2 suppliers produce superior quality product to those of the last 2, by considering the supplier partition that separates superior ones from inferior ones, we have the following performance comparison. Note that the best partitioned sub-reserve performs better than the best regular sub-reserve when the quality difference is large. So the main takeaways of this talk is that first, we characterize the optimal pay-as-bid assortment on a symmetric generalized affine demand model. And in the process, we established a novel class of assortment rules called K-sub-reserves, which are intuitive and easy to implement. We showed with examples that K-sub-reserve rules can be effective in practice, even with incomplete or limited information. And lastly, we show natural generalizations of K-sub-reserve rules can perform well even in asymmetric settings. So, thank you.